All right, so let's start. It's a long time for, from our last lecture. It's like a month ago. We have 2 weeks spring break and 1 week for exam, so it's pretty a long time. And this is the first time I try to teach on online, so I need to get familiar to how I can teach it. And if you guys has any question, for what I'm talking here during the class, just speak out directly. Okay, just talk to me directly. And I know that Zoom also allow you can chat text the message on the chat during the chat. So please do not ask me the question on chat, okay? Because I may not have time to check it out. So if you have question, just interrupt me and ask me directly. And because we have a small class, not a lot of people, I think this way should be better. So today's topic we will start the natural convection. We already finished the forced convection, and the forced convection we finished for the forced convection on external flow. Basically, the laminar boundary layer theory we go through, and also the forced convection for internal flows, and which is the laminar flows inside the pipes. We finished that part, and now we are going to the natural convection. The biggest difference between the forced convection and the natural convection is that in forced convection, there's some force to push the flow to moving. The flow motion is pushed by either a pump or a fan or any other pressure gradient. And so there is external force to push it. Okay. And the natural convection is different, actually. So here is the definition of the natural convection. Basically, it's the fluid motion is caused entirely by the buoyancy forces. And this buoyancy forces is rise due to the density changes of the fluid, and which is a result from the temperature variations for the fluid in the gravity field. Okay, so the driving force in this case is gravity. Okay, is the gravity here. Let me see. This is a gravity force here to give you the driving force for the fluid. And this is an example of the natural convection. This black body is a heated surfaces, and we put it into an air without velocity, okay, in the stilled air. And because it's heated, the air close to the body, close to this heated solid, close to the wall, their density will reduce because the temperature is increasing. And we know that due to the buoyancy, the temperature, when density is decreasing, the air will moving to the top, it's moving on top. So this will induce a velocity field, which is moving from the bottom to up. And so this velocity will keep increasing, all right? And it will, and the outside of this, it will create a thin layer, okay, where the, where the air is affected by this buoyancy flow. And this thin layer looks similar to what we see in the forced convective laminar boundary layer. So we can also think that this small region here is like a natural convection boundary layer. And inside this boundary layer, we have the fluid moving from the bottom to top. due to the this buoyancy effects. And at some point, this velocity can even bigger enough so that the flow field inside this boundary layer become turbulence. So this is one example we can have the natural convection. So basically for this natural convection, we need a driving force, right? Driving force. And this, in this case, the driving force is the gravity. Okay. Okay. Oh, I don't know why I cannot write it clearly. Actually, this gravitation. And this gravitation, gravity force giving is the driving force that causing this fluid to move, and that's why we call it natural, because that this gravity is existing, naturally existed natural. It's so hard to write. Okay. And natural convection is not only existed in the gravity field. Okay, actually you can have any external forces. Okay, the body forces, which can create the force due to the density changes. Not only the gravitation. One example is this picture here. Basically, in this picture, there's a rotor and it's rotating around the axis. And if we have a small, container and has a fluid inside, we will also see. You can also see that the fluid is moving from the smaller radius region to the larger radius region and circling back. And in these cases, actually, this natural convection is caused by the centrifugal. I don't know why I cannot write this tree. One second, let me check what's wrong with my device. Tree. So okay, so let's go to the top. So it's working well last time. It's not working well this time. This drawing part. Tree. Okay, it's not totally cannot write it. Tree. Seems working. Okay, I know what it is actually. So the issue is that where I write it, let me erase everything. Okay. Let's put it here. So the driving force. So if it's a gravity, right here. Yeah. Cannot write it. Okay, so let me just speak. So not writing. Okay. So if the driving force is the gravitation force, we call it natural convection because we know that the gravity is existed naturally. Okay, it's we can see it's a natural force. And an example I'm showing here, this is when we have this rotating and the natural convection can be caused by the centrifugal force actually. And we can also have other forces, okay? But for this centrifugal force, it's not natural actually. because that is we manually rotated this rotator, so create this convection things actually. And in this case, it's actually people just calling this free convection. So we always think that okay, natural convection is also called free convection, but sometimes okay, people just think that only the convection caused by the gravity force actually can be considered the natural convection, and all the convections causing by the other field force like this centrifugal force, we call it free convection. So in literature, some people making this difference, but generally speaking, okay, we can just consider that the natural force is also called natural convection is also called free convection. And to study the natural convection, we start from the governing equation. And the most common problem for natural convection is the if you have a heated vertical plate, okay? So we have a plate here, and is vertical, and we have the gravity field actually, and this is the boundary layer caused by the natural convection, and outside the boundary layer is free stream air, and it has the temperature T infinity, and the air has no velocity, so it has 0 velocity here. And we set this along this plate as the x direction, and vertical to the plate to the y direction. One thing you need to know that in the textbook, the textbook using y direction along the plate and using x direction for the vertical to plate. I didn't using the same notation as the textbook here. So if you check the textbook, you can see that the equation here, x and y, actually in my notes is inverse, actually is reversed comparing to the textbook actually. So this is so the governing equation is very close to the forced convective boundary layer problem we saw before for forced convection laminar boundary layer. Only except a few terms is different actually. This is continuity equation, and you need to realize that the density is inside this differentiation operator, okay, differentiation. Actually. So reason for this is that one important thing you need to know that we need to realize that this rho is not constant, okay? In the natural convection. So that's the reason that we cannot put the rho just outside and just remove the rho directly. So the rho has to be considered in the continuity equation. And for the momentum equation, we have this convection term, rho u and rho v term. We have the pressure term, and also we have the viscous term, or you can also call this friction term, this term here. And similar to the boundary layer problem we saw before, okay, for the forced convection, we only consider the significant velocity gradient in the y direction. For this partial x term, partial x term, this term, we assume is close to 0. Okay, so this term is gone. So that's the reason that you only see this u viscous term on y direction. We didn't say we neglect the x direction changes. And one additional term is in the momentum equation is this gravity term, rho and rho times g. So this is the additional term we have here. And all the other term, all these convection term, pressure term, and viscous term, they are all same comparing to the forced convective laminar boundary layer problem we saw before. only this rho times g is the additional term we have here. And also again, because the pressure inside the boundary layer and the pressure inside the free stream should be equal in the x direction, because they should be hydrostatically equal, okay? And if we consider if you put the Bernoulli equation for the flow outside the boundary layer, we can calculate that the pressure drop on the x direction actually will be balanced with the gravity force actually. So we bring this pressure drop equation to this x direction momentum equation here to repeat it to replace this dp over dx. So we can get the final form of the momentum equation, which is this is the convection term, rho u partial x plus rho v partial u partial y. And we have the viscous term here, partial y for the mu partial u partial y. And this is the additional term we have here, which is contains the effects of the buoyancy. And the last governing equation is the energy equation. And for energy equation, actually it's exactly the same with the one we see in the laminar boundary layer for the flow over the flat plate. So we have the convection term, and we have the thermal diffusivity term. So this is equation is exactly the same. So in summary, okay. So comparing all these three equations, comparing with the governing equation we saw before in the laminar boundary layer for flat plate, the only difference is there are only two differences. One difference is that this density here, because the density is not constant, it has to be included into the this gradient operator, sorry, divergent operator. The second difference is that we have this additional buoyancy term due to the gravity in this x direction momentum equation. And the y momentum equation is similar things to that laminar boundary layer theory. Is that basically is showing that the pressure term is only a function of x, not a function of y. So we just neglect that term. So we have three equations: continuity, momentum, energy, and we have we do not know rho, we do not know u, we do not know v, and we do not know the temperature T. Okay, so this is what we need to solve. So definitely we have three equations, 4 unknowns. So this is the 4 unknowns. So we do not have enough information to solve the problem based on this equation. And then this is how we can solve this is coming to the method called so-called the Bosniak approximation. And basically it's an approximation that can further simplify the governing equation we saw on the previous slide, and to make the problem easier to solve. So the assumption contains two parts. Okay, basically it's two assumptions. The first assumption basically is saying that we can neglect all the variable property effects in the equation, in these three equations, except for the density in momentum equation, which means that the density in this continuity equation, we can still consider in continuity equation, we can still assume this density, approximately constant. So for continuity equation, you can take this rho out and delete and remove it on the both sides. But you cannot do that for this. But the density here in the momentum equation, this rho here, you cannot consider it as a constant. And how we can see how this rho here, rho infinity minus rho, this rho is not a constant. So what will it will be? And that is for the second assumption here. Basically saying that the density difference, the density difference term can be simplified to this rho infinity minus rho equal to rho times beta times this temperature difference. And this beta is the so-called volumetric coefficients of thermal expansion. And if you're familiar with this thermodynamics, actually this beta is a thermodynamic, is derived from this the definition of this beta in thermodynamic in our previous thermodynamic class is should be defined as 1 over rho partial p of partial t. Sorry, not partial p, partial rho. Partial rho partial t when pressure is constant. Okay, so this is a definition of the beta from the thermodynamic side of view. And if it's a ideal gas, which means that you can consider that P equal to rho RT for ideal gas. And beta just equal to 1 over T actually. So with these two assumptions, and the first assumption tell us that, for the continuity equation, you can just assume the density is still constant. So you can remove the density there. And for the momentum equation, density not a constant, and this density changes can be related to this temperature changes, temperature difference corresponding to this beta value. So there's a typo here, sorry. Let me correct it. So just there's a typo here. So this is not a rho, this should be G, okay? It doesn't allow me to write it there. Oh, I can do that. So just let me rewrite it, okay? So this is not correct. It should be rho infinity minus rho equal to G beta T minus T infinity. So this is wrong here. And this is the correct one, okay? Okay, here. All right, so substitute this equation, rho infinity minus rho, back to the momentum equation we have before. This momentum equation before, and so rewrite all three equations. So this will be the new governing equation we got here. The continuity equation you saw it here is that there's no density anymore. And for momentum equation, you see that this buoyancy term is related to the temperature field. And we also have this the energy equation not changing. So in these cases, we can see that the unknown we have is U here, V and T here. Okay, so we have three unknowns and we have three equations. So the problem can be solved at this point by using this Bosniak approximation. To solve the equation, we also need the boundary condition here. At y equal to 0, which is at the wall, we know that there is no velocity. Both u velocity and v velocity will be 0. And the temperature can be a wall temperature. It can be either constant or a function of x. When y go to infinity, is very far away from the wall. It's also u and velocity. There is no velocity there because the free stream air is there's no velocity there for the free stream air, and the temperature that the free stream air will be T infinity. We also will have a x equal to 0 location initial condition, where u and v will become 0. So this is the starting point where the net boundary layer will be, okay? And the temperature will be equal to T infinity. So with this equation and this three boundary layer, so we should be able to solve the problem. Okay, any question here, guys? It's so quiet. Any question?
No.
Okay. Yeah, don't afraid to talk, okay? Because this online teaching is my feeling is really different with this teaching inside the classroom because I cannot see you, and you know, I sometimes when I teaching I even worry about that. You know, you're so quiet on your side. Maybe I'm worried about if I drop my internet connection. I even do not know that. You know, so if you have any problem, just speak, just talk to me. All right, so this is the current equation. So how we can solve the problem? Let's go back to remember to what we did for our previous problem, right? For the flow over the flat plate. You know, this laminar boundary layer problem, the false convective boundary layer problem. We have this delta here, and or we can have another delta, delta t here. So we're using several ways to solve that problem, right? You remember we do the scaling analysis. We do the scaling analysis, and we also do the integral method. We also do the similarity solution, right? Similarity solution. Sorry, this pen is not really working well actually, so it's not writing well. I don't know why actually. So for this problem with this equation and this boundary condition, we can also do these three things actually. First, we can do the scaling analysis for these equations. And so by doing scaling analysis, we can knowing that, what the thickness will the boundary layer, the magnitude for the boundary layer thickness, what the magnitude for the Nusside number, those kind of things. And also we can do the integral method, like we do an integration, do the integral form, develop the integral form of this momentum and energy equation, so that the wall, the viscous force on the wall and the heat flux at the wall can be calculated. Or we can try to, do the similarity solution. Just assume that the velocity profile and the temperature profile inside the boundary layer, they are similar along the x direction, along the plate direction. They have the similar profile, and then after we do that, we assume similarity, we can, assume some similarity variable, and by substituting those similarity variable into these three equations, we can obtain we can combine all these three equations in a 1D, in a ordinary differential equation, which we can obtain the exact solution. So we will go through one by one here. So the first thing we can do is to do the scaling analysis. And look at this picture here. So we assume that this plate has a length of h, and this boundary layer, the thermal boundary layer with will have this delta t here. So from the continuity equation, we do scaling. The u velocity will be right here. Okay, so this will be it doesn't allow me to write. This is u, this is v. Okay. Let me remove this. It's not working. So the u velocity is the velocity on x direction, and the v velocity is velocity on the y direction. So to do scaling analysis, U will be on the length scale for the U x direction will be h, this plate length, and for v velocity, their length scale will be the delta t, this boundary layer thickness. So we have this u h is the same order of v of delta t. This is from the continuity equation, and from the energy equation here, and we can have this u times delta t over this h length scale for the x direction, and for v times the delta t over this length scale for the y direction, which will also be the boundary layer thickness. And the delta t here is equal to t wall. I don't know, this really affect me. Minus t infinity. Okay, this is the delta t, the definition of delta t. Alpha is thermal diffusivity, and this partial t square over partial y square is the order of delta t over this delta t square for this distance here. And because this u over h has the same order of v over delta t, so you can see that these two terms here, this u delta t over h, this v delta t over small delta t, they are the same order, these two. So basically what I mean is that if you bring this equation into this one here, and you will get that this two term, this term and this term, they are the same order. Okay, they are all equal to this same order. Okay, and so that's why that means that the two convective terms has the same order here, and it has to be the same order on the right hand side, which is this thermal diffusivity terms. And by equaling these two terms, we can know that the velocity scale, okay, the u velocity scale should be approximated as the r times h divided by delta t squared.
On the right side, where it says delta t.
This delta t is this length of this boundary layer. You're seeing that for this natural convection, we also have some boundary layer created actually, and you only have the flow velocity inside this boundary layer.
So it's Tw minus T infinite.
You mean this delta T?
Yeah.
Delta T is a Tw minus T infinity.
Okay, thank you.
Yeah, W is the wall temperature. I think my software has some issue because this you to write very well. I don't know why. Okay, and then let's go to the momentum equation. Similarly we do the scaling analysis for all these three terms. And the momentum equation, we have these two terms is the convective terms, and this mu term is the viscous term, or you can also call it friction term, and this is the buoyancy term. For the convective term, u will still be u partial x can be order of u divided by h. H is this plate scale, and for this convective term, v times u over y direction scale will be delta t. And similar things, if you substitute this continuity scaling result to these two convective term, you will see that basically they are the same order of u squared over h actually. And for the viscous term, you have mu here, and u divided by delta t squared. So basically for this viscous term, this mu partial u squared partial divided by mu. So let me try to fix this pen a little bit because I really need to write this thing. Let me check what's wrong here. And I think this can show cursor. Bear with me. So we have to. We do not have this pen setting, so what's the name of the software to set this? We do not have it here, so we can set it. Let me write it here. Can I write it? No, it does not allow me to write. Okay, you can. I can write it here clearly. Okay. So, guys, give me 1 minute. Okay, 1 minute. Let me search something. So, where is it? Where is it? Citing. Apps. And so what is common? Extension, using CBS audio, notes. Okay, I know it. So open tablet is this one. Let me see if this looks better now. Okay. Okay, so now I should be able to write it. Okay, so let's go back to here. Let's sorry for the waiting. So for this mu, okay, so now it's writing much better. We this partial square u and partial y square term. So this is order. If we do the magnitude analysis, it will be mu of u divided by delta t square. Okay, and then you bring, because we know that from this result here, we know that u is the order of alpha times h divided by delta t square. So this again, you just replace this u here with this result. So we will get this alpha h divided by delta t, fourth order of delta t. And that's why result, that's why we got this result here, mu times alpha times h divided by delta t to the power of 4. Okay. So let me clear it here. So now we have 3 terms here. And for the boundary term is just the g times beta times delta t. Again, okay, for this u square, we can also replace this u with this value here for this convective term. So the convective term can be finally writing as this way. And if we also divided this g beta delta t on the both sides, so we can write that in this term here. So for momentum equation, we have three terms here by doing this scaling analysis. So this is alpha square times h over delta t is 4. And so this is the convective term, this buoyancy term, and this is the friction term. And if we can rewrite all these terms, okay, so this is will bring this definition of so-called the Rayleigh number, which is g times beta delta t times the cubic of h length scale divided by alpha thermal diffusivity, and also divided by mu. This is kinetic viscosity. And you rewrite this one, and this one term here, you can relate it actually. This term can be equal to this one, which is the reciprocal of the Rayleigh number times the reciprocal of the Prandtl number. And also there is a scaling form between h over delta t to the fourth power order. And also this term can be rewritten related to this Rayleigh number term. Okay, so now we have three terms. We have this convection term for scale after scaling, and we have this buoyancy term, which is order one. We have this friction term, which is also a function of Rayleigh number. So the next analysis of these three terms, the scaling will including to see that the effects of the Prandtl number. We need to distinguish the cases that when the Prandtl number is much larger than 1, or Prandtl number is smaller than 1. Why we do that? Because now we have three terms. Because when we do the scaling, we only need to, so final we only need to get two terms. So there is one term is the additional one. And if we consider this Prandtl number here, in this convective term, if Prandtl number is much larger than 1, okay, seeing this Prandtl number is a very big number. So basically the convective term, because this is a 1 over Prandtl number, so this term will go to 0. And which means that the viscous term should be order of 1. These two terms has to be equal, or has the same order, okay? So basically I can write it here that if the Prandtl number is much larger than 1, so basically it's telling us that your viscous term is the same order of buoyancy. Okay. And if Prandtl number is much smaller than 1, which means that this term will go to very large because it's 1 over PR. And this term, so this term, after this term going to be very large, very large number. And the only way that this three term can be equal is that only this term, convection term, has the order of 1. So basically means that when Prandtl number is much smaller than 1, the convective term will have the same order of buoyancy. Okay. So this is what we, and after we analyze this momentum equation, do the scaling analysis for this momentum equation. And let's talking about this Rayleigh number, okay? This Rayleigh number is, you can see in here that basically contains the effects of the gravity, because we have the gravitation G here. And also we have this thermal expansion coefficient beta here times delta T. So this is basically on the top of this term, basically including the buoyancy effects. And on the bottom, basically we see that this is alpha is thermal diffusivity and this mu is viscous diffusivity. So this is basically a buoyancy effects over the diffusivity from both thermal and viscous actually. In the let me go to the next page. So let's from the case one, okay. When we have high Prandtl number, which Prandtl number is much larger than one, which means that you know, in the convective boundary layer, we know that this means that the velocity boundary layer thickness is much larger than the thermal boundary layer thickness. And from our analysis here, so if the Prandtl number is much larger, so these two terms have to be the same order. The viscous term and the buoyancy term have to be the same order. So we comparing these two terms. So if we write those two terms, let me write it clearly so that we didn't get lost. So this H divided by delta T to the power of 4 of R of A of H minus 1 times Prandtl number minus 1. So this is the convection term. So this is going to 0. And this order of the same order of it has the same order of 1 buoyancy and the viscous term H of delta T divided by 4 times R A H of minus 1. So these two terms have to be same order. So basically means H of this delta T to the power of 4 times this R of A of H minus 1 has the same order of 1. And if we rewrite this one, so this is here, the things here we show in here. And if we write this one, we can write this delta T because we have the thickness of the thermal boundary layer will be equal to H of this RAH of minus 1 divided by 4. So this is why we got the boundary layer of the thermal boundary layer. And for the U velocity, for the velocity boundary layer, basically we need to know this U value. And from our previous scaling result here, we know that U is based on energy scaling, we know that U is order of this R times H divided by delta T squared. So U equal to alpha times H divided by delta T squared. And you can bring this result delta T, this result here, this result back to this U velocity result here. You can know that the final result, this will be the U value. Okay, so U will be equal to alpha H of delta T squared. And since delta T is this scale H times the release number to minus 1 over 4 power. So you bring this delta T into this result, you will get that, I should not using the equal sign, just using the approximate sign. So this will be approximate to alpha of H times the release number H 1 over 2. Okay. So let me clean this thing there. So this is the two important result we got from this scaling analysis when Prandtl number is larger than 1. It's telling us that what is the U velocity will be. The magnitude of U velocity will related by this reading number times alpha divided by H. So this this U value telling us that what this velocity boundary layer will looks like. And on the other side, we know this delta t, which is the thermal boundary for the thermal boundary layer. And further, you can further write that after we know this delta t equal to this h times RA release number to the power of minus 0.25. You can also derive the Nussbaum number based on this thermal layer boundary layer thickness. The way to do this is because we know from the energy balance, the conduction at the wall, which is dt over dx at y equal to 0. This is at the wall, should be equal to the convection, right? H of T of wall minus T infinity. Okay, and if you do the scaling of this equation, basically telling us that K times this delta T divided by this delta T with the same order of H of delta T. Okay, and then it's basically this telling us that H is the order of K over delta T. Okay, we should already know this because we also see this correlation in our laminar boundary layer theory. So the film coefficient H is the magnitude of the K divided by the thickness of the boundary layer. So therefore, because we know this delta T here, this delta T result here, you bring this one into this equation, you can calculate this Nussbaum number result, which is defined Nussbaum number based on the plate length h small h times big H divided by K. It will just to the radius number to the power of 0.25. Okay. So with these two results, we can draw that we can analyze the profiles for both velocity and temperature inside the boundary layer. So this is what the boundary looks like actually for these cases, because that we have this Prandtl number much larger than 1, which means that the velocity boundary layer is much larger than the thermal boundary layer. Okay, for the thermal boundary layer, this is smaller region. You can see that if the wall temperature is larger than the free stream temperature, so basically the temperature profile is gradually decreasing from the wall temperature to this free stream temperature. But for velocity, it's different. Velocity is the profile is not monotonically. Actually, the velocity profile, it will increasing first because at the wall we have 0 velocity, right? And it will be due to this buoyancy effect, it will increasing first to your maximum value, okay? And then it will start to decreasing again, and until it reaches to the free stream, because we also know that at the free stream we also have no velocity. So this is a special things that we can see in this natural convection. Remember that for this free for the flat plate for the false convective boundary layer. So if we have this velocity profile, so this can be the velocity profile, right? Velocity just increasing from this wall 0 value to the free stream value here, u infinity. So the profile of the velocity is monotonically increasing, okay? But in this free stream, in this free convective boundary layer, you can see that the velocity actually is increasing first, reach to a peak value, and then decreasing. Why? Why this happen? The reason is very simple, because that the complication we have for the momentum equation, because we know that basically the momentum equation gives us the result of the velocity. For moment, if we go back to see the momentum equation, the reason it becomes complicated for the velocity is that in the momentum equation, we have 3 terms. We have this convection term, we have this buoyancy term, and we have the viscous term, okay? And for our previous problem, like this convective boundary layer, false convective boundary layer, the momentum equation only have two terms, only have the convection term and the viscous term. So only these two terms need to be balanced. But for this free convection, we have three terms in the momentum equation. And all these three terms need to be balanced. And how it can be balanced? Basically, it be balanced in two regions. We can draw in here, in these cases. Inside this thermal boundary layer, we can call it the heated region. In this region, the buoyancy effect basically will be balanced with this wall friction for the buoyancy effect. And in this and outside of this outside the thermal boundary layer, in this region here, we call it unheated region for velocity field. Okay, because this delta velocity boundary layer is much larger than this temperature boundary layer. And this unheated region, because there's no temperature, right? You see that the temperature is gone. Because we only have the buoyancy when you have the temperature difference. So at this region, there's unheated, there's no temperature difference, which means that there's no density variation, and then there's no buoyancy. So in this region, we do not have any buoyancy effects. So in this region, it just like go back to our original this problem. In this region, because there's no buoyancy, that's three terms in that momentum equation. You only need to balance between the wall friction term, that mu viscous term, with the convection term. Okay, so basically means that this we have a very special, we call this two-layer structure. Okay, so this is a very special thing for the this natural convection boundary layer. We only see this in this natural convection boundary layer. And let me remove this. Let me write down what I write it here before. So in the heated region, your friction effects, your friction term will need to be balanced with buoyancy. All right, because buoyancy effect is strong because that you have large temperature difference in this temperature boundary layer. And it also is because it's close to the wall, so the friction effect is strong. And in this unheated region, it has to be the friction balanced with the convective term. So we also call it the initiative. Okay. All right. So now we have this U scale for the U, which we know the velocity profile looks like, and we also know the scaling for this Nussbaum number. The temperature, basically, this telling us what the temperature boundary layer would like, and we can consider that this is in unheated region. Okay. So in unheated region layer, there's no temperature, and the length scale become from delta T to delta. Okay. And because we know that in this term, in unheated region, the friction term need to be balanced with the convection term. So this is the convection term, U square over H. If you look at the previous term, so this is the convective term, U square over H here. And this is the friction term, which will be mu times U divided by delta square. So we can also develop the magnitude for the velocity boundary layer, this delta here. So we can know that the delta will be the order of mu H over U. And because that we know that the U velocity because we know that the u velocity is order of alpha h over delta t square, and u velocity equal to this. Also, we can further can write this alpha h over h times release number to the power 2. So basically, you bring this u value to this to replace the u here. You can basically also derive that the magnitude of the velocity boundary layer, which will be h times release number to minus 0.25 and times the Prandtl number to the power of 0.5. Okay. So basically, this is the three important results we got here is that this result here, this result, and this result. This is the three important results we got from the scaling analysis. This is telling us that, and also this one, sorry, and this 4 results is important. So it's telling us that by doing this scaling analysis for this high Prandtl number fluids, we can know that you know the boundary layer thickness, the thermal boundary layer thickness is it should be some function of this some constant times this h times Reynolds number to minus 0.5, and the velocity boundary layer thickness will be changing with an additional Prandtl number here, 1 over square root of Prandtl number here, and also that we know that the maximum velocity, this u, in the magnitude of this velocity, induced velocity due to the natural convection, can be the order of this alpha over h times release number 1 over 2. And the overall Nussbaum number for the plate will be just the order of release number of 1 over 4. So with all these scaling results, so if we can do experimental analysis, if we can do an experimental analysis, so we can just try to determine that what the additional coefficient c here for each term, right? We can know that the Nussbaum number will be just some c times the release number to 1 over 4. So we just need to find this constant things actually. So this is why we do the scaling analysis. So this is the case that when the Prandtl number is much larger than 1. All right. So now for the low Prandtl number cases, when Prandtl number is much smaller than 1, and we know that in these cases from our previous laminar boundary layer theory problem, because Prandtl number is much smaller than, because Prandtl number is mu of alpha, right? So Prandtl number is much larger, much smaller than 1, which means that mu viscosity is very small. So which means that your velocity boundary layer will be small, right? And thermal boundary layer, because alpha is relatively is bigger, so your delta t for the alpha will be bigger. Okay, in these cases, let's do the scaling analysis, right? And in this case, let's go back to here, this term, this result here, because Prandtl number is much smaller than 1. So this term here has to be order of 1, and this term can be neglected. And by doing that, so this term has to be, the convective term has to be order of 1. And this u result is from the energy equation here. And with these two results, we can derive the new correlation for the magnitude for the thermal boundary layer thickness. So delta t will be equal to this value. And if you compare with our previous cases, this delta t equal to h times real number to power minus 0.25. You see that it only had an additional Prandtl number here. Okay. And sometimes we also define a new dimensionless parameter, which is called Bosnick BOUSSINE Bosniak number. So it's B of O will be equal to its release number, okay, on the X coordinate, X times print number, okay. So we can define a new dimensionless number for this product, which can be called the Bosniak number, okay. And you bring this delta T results for this low print number fluids to this U results. You can get the, you can know that this, you can know that you can find that this U velocity, what's the maximum U value in this boundary layer, the magnitude of this U induced velocity in this boundary layer will be. And similar things you can develop the value for the Nussbaum number. And the way to calculate this Nussbaum number is similar things than the way we did it here, because H is the order of K or delta T, and Nussbaum number is defined by H times big H divided by K. So it's similar thing. That's H over K divided, and you're just using the same way we derive it. You can derive that the Nussbaum number is the reading number times print number. It's also basically the you can also write this as a Bosniak number. This can also be read as a Bosniak number. Okay, so with this velocity and this velocity result and thermal, Nussbaum number results, we can also draw the profiles looks like inside the boundary layer, this natural convection boundary layer, when the print number is small. And definitely we have this, we know that a thermal boundary layer will be larger than your velocity boundary layer. And your velocity profile will also increasing first and reach a peak and then starting to decrease. Okay. But we also can define a small region, okay, which we call that the distance from the peak of the induced velocity field to the wall, and we call it delta of V. Okay, this is not the velocity boundary. It's just the additional spatial, spacing. Okay, delta V distance basically is defined as the peak of the velocity profile to the wall. Actually. And by using this delta V value, we can also separate the boundary layer into two regions, the region 1 and region 2. So in region 1, where this Y value is smaller than this delta V, okay, in this region here. And we have three terms in the similar like before, okay, as before. We have three terms in the momentum equation. We have the convection term, we have the buoyancy term, we have the viscous term, or you call it friction term. So in this region 1 is basically we have the friction term will be same order of buoyancy. Okay, and in the region 2, where is delta V smaller than 1, smaller than delta T. Okay. In this term, basically is your initial term. Initial term is just the convection term, okay? Because initial force is coming from the pressure force. So this will be equal to buoyant OY ANCY. Okay, so it's the initial force. In this term here will be initial term will approximate to the buoyancy term. Okay. So let's consider in region 1, okay? I do not need this. So let's consider in this region 1 here, where the friction will be the order of the buoyancy. So this is the friction term, mu times U divided by this small delta V square. Okay, because it's partial, because of the viscous term is mu partial U partial Y square, right? So, and U should be this one, and the Y scale becomes to the delta V. And it will be order of the buoyancy, so will be order of G beta delta T. By doing this scaling, we can derive that what the length scale of this small delta V will be. And it will be mu times U over the G beta delta T and the square root of them. And also we know that the U velocity here, we have this U correlationship already. And substitute this U correlationship into this delta V. We can get the final results, which this small delta V scale will be equal to this result. H times the Reynolds number divided by Prandtl number to the 1 minus 1 over 4. Okay. So this telling us that this after knowing this because this scale delta V is very important because that from this scale we can know that this double layer structure, which layer is which part, what to which region is layer 1 and to which region is layer 2. Okay. And one thing you need to know that this Reynolds number divided Prandtl number can also introduce to another dimensionless number, okay, which is called the Groshof number. So let me write it here. Grashof number. Grashof number. So which is defined as G of R of X will be equal to this RA of X divided by Prandtl number. Okay. So basically, in the natural convection, okay, we constantly seeing 3 numbers, okay. We constantly seeing that, this GR will be equal to RA release number divided by Prandtl number, or we can see the reading number, or we can see that this Bosniak number will be RA times PR, okay. So there are these 3 number, this 3-dimensional number, the Grashof number, the reading number, and this Bosniak number. They are closely related, okay. The difference between them is just the Prandtl number. And the Grashof number is just release number divided by Prandtl number, and the Bosniak number is just the reading number times the Prandtl number. Okay, so that's why is that when you see this reading number divided by Prandtl number, you can rewrite it as just as the Grashof number to the power of -1 over 4. Okay, and in this cases, if you can divide it by this delta V over this delta T, you can get this Prandtl number 1 over 2, which is much smaller than 1. You know that this result is much smaller. This delta V will be much smaller than delta T. Okay, so this is the cases of the low Prandtl number fluids actually for the scaling result. I know that you guys maybe a little bit because there's so many results here, final result here, and for both cases, large Prandtl number and small Prandtl number. So it's better that we group all the results together, so that in a table form. Okay, so this is a table form looks like, okay. By doing the scaling. So this is the delta T result when Prandtl number larger one, Prandtl number smaller one. And this is the distance from the wall to the velocity peak. Okay, so this is delta V, okay, not delta U, this small delta V there, which we introduced before. And this is the thickness of the velocity field, okay, velocity boundary layer is delta. And this is the maximum of the induced velocity, U, and this is the Nussbaum number. So you can see that for Prandtl number larger than 1, it's basically the combination between H and radius number. And for Prandtl number smaller than 1, you will usually the results comparing to here, you need have an additional Prandtl number here. So this is the final result here. And this is a picture from the textbook. Okay. And this is when the prandtl number is smaller than 1. Okay. When the prandtl number is smaller than 1 in this region. So this curve that tell you that what the delta T, the thermal boundary layer thickness will be. And this term will tell you that what this delta V value will be. Okay, when prandtl number is larger than 1, this curve telling you that what the velocity boundary layer thickness will be, and this term tell you what the thermal boundary layer thickness will be. And they are all, the y coordinate is this h times the radius number to the power of minus 0.25. So this is a summarization of the result. And you can also additional having the result for the Nussel number. Okay, because previous so if you use the Nussel number divided by this radius number to the minus 1.4 to the power of 0.25. So when prandtl number is smaller than 1, you will have a 1/4 correlation to this. And when prandtl number is larger than 1, so it's you just equal to this value will be just equal to a constant, because this because the result we have in the previous one, because these two results here, prandtl number times this one, these two results you just join there. Okay. And the reason. Okay. And what's this? Okay. And the reason you see this 1/4 because this is a log scale. Okay. And the log scale you have 1/4 basically. That means that why you have this 1/4 powers for this prandtl number here. So this is the scaling analysis. And now you're looking at this result here, we're showing here. And can you just let's remember that what we have result before for our laminar boundary layer, right? For our laminar boundary layer, we have this delta over x will equal to Reynolds number of x of 1/2, right? Minus 1/2. You remember this? So if you're comparing with this result here, okay, delta or delta t is same thing actually. So basically, you can see that this is for our previous laminar boundary layer for false convection, convective heat transfer. And for this natural convection, basically you can write that this delta T over H will be equal to release number to the minus 1/4. If you replace this H, okay, to some X value, you can also write an X value here. So what does this mean? This means that the really number, this really number we're seeing here, the row of this really number is just similar to the row of the Reynolds number to the this row Reynolds number to this laminar boundary layer in the false convection. Okay, so this is some equivalent. Okay, if it's a false convection laminar boundary layer, is Reynolds number telling you that what's the boundary layer thickness, and if it's the natural convection, is the really number. This really number tell you the boundary layer thickness. Another thing, we also know that the Reynolds number also telling us that in this laminar boundary layer, right? This laminar boundary layer. So we have this here is a laminar field, and then it maybe suddenly become the turbulence. So this can be turbulence, and this is laminar. So is this Reynolds number value? So at this point, maybe we have this RE of X at critical. Okay. Basically, what I want to say is that Reynolds number also telling us in these cases which region is the laminar flow and which region is turbulent flow. It actually there will be a critical Reynolds number telling us if the boundary layer is laminar or turbulent. Okay. Similar thing. This really number also can behave as a parameter, okay, will telling us that the flow region will be. Let me go to our first page here. As we seeing here, right? So even for this natural convection, we may also have it may also develop to the turbulent flow later on. Okay? It may also consider both the laminar flow region and the turbulent flow region. And this reading number can also be used to determine, if the flow region, what flow region it will be, it's laminar or turbulent. So we can also set a critical reading number to determine the flow region. And we will talk this part later on when we go to the talking about the turbulence convection. Oh, okay. Yeah. Okay, so, all right. So let's go back to this 3 parameters we commonly use, right? We're telling us that we have this reading number. And we have this Bosnian number. And we also have this Grashof number. And their correlations is also given here. Is also given here. The Grashof number is basically real number divided by Prandtl number, and the Bosnian number is basically the reading number times multiplied by additional Prandtl number. And there's a meaning, okay? The physical interpretation of this dimensionless parameter can also be interpreted by using the length scales, okay, different length scales, okay. Based on the result from this table, okay, you'll see that this radius number of minus 104 basically is delta t over h, okay. So we can see that this radius number we can consider is at the wall height divided by thermal boundary layer thickness of delta t, okay. And this Bosnian number can be also interpreted, physical meaning can be interpreted as the wall height divided by thermal boundary layer thickness of delta t when Prandtl number is smaller than 1. And this Grashof number to the power 1 over 4 can be interpreted as the wall height over the wall shear layer thickness. And this wall shear thickness, delta v, as we said, is the distance of the peak of the velocity profile to the wall. Okay, this is the delta v when the Prandtl number is smaller than 1. So basically, this is another way you can show what's the physical meaning of these 3 dimensionless parameters. Okay. Any questions? So we finished talking about this scaling analysis. Do you guys have any questions? Anyone?
No.
No. Okay. I hope you're not lost here. And let me erase this so that. Let me erase this one. So I will share this whole notes I show here, and also this other notation I write, and on the blackboard. So you really do not need to copy the notes yourself actually. Okay. And then after we talking about the scaling analysis, we can try to get the real solution, right? We have 2 ways to do this, similar to our previous boundary layer problem theory. We can using the integral solution, or we can using the similarity solution. So let's start with the integral solution. So this is the momentum boundary layer, and so this is x coordinate. So this is x location. This is x plus delta x, and the velocity profile on this momentum boundary layer, or velocity, we can also call this velocity boundary layer, is this 2-layer structure is increasing first and decreasing. Okay, and as a free stream, there is no velocity, so it will be 0, and we create this integral control volume starting from y equal to 0 to y equal to y, and starting from this smaller x to x plus delta x. Okay, so we can integrate we can do integration on this momentum boundary condition, momentum equation on this control volume here. And we also have we can also do the thermal boundary layer, which the temperature is decreasing from the wall temperature to the free stream temperature monotonically. And we can also draw the same integration control volume from y equal to 0 to y equal to y, and from smaller x to x plus delta s. And so, yeah, overall, okay, we want this y value. So we do this integration for this integral method can be larger than both delta and delta t. Okay, so this y value here has to be in the free stream, can be larger than this delta and delta t. So now we can do the integral method. Okay, so first we try to derive the momentum integral equation. To derive it is the same procedure as we did before for the boundary layer theory. So basically is that this equation 1, the continuity equation, you times the u on this equation and plus and added it to the equation 2. So you're using 1 times the u plus 2. So this is the equation you got here. Okay, and you integrate this equation. You integrate it on the y direction from 0 to y, and you all notice that you have the following boundary condition at the y location. It will be free stream. There's no u velocity, and also at the y direction, it's free stream, so there's no gradient on y direction. And on the wall, u at y equal to 0 and v at y equal to 0 are both 0. So you integrate from 0 to y on this equation on both sides. So basically you get this equation, this d of dx, you still have it, and but you integrate the u square for this one, and for this one is partial y term, you integration on y, so it basically will be the uy vy minus u0 v0 for this term. Okay, uy u0. And because uy equal to 0, because we know that u0 v0 is 0, so this term and this term is basically all 0. Okay, all 0. So these two terms is gone. And you also can integrate this buoyancy term between 0 to y, t minus t infinity over dy. And also you can integrate this second order y derivative term. So basically it will be mu partial u partial y over y minus mu partial u partial y over 0. Because we know that at the y location, there's no gradient on y direction because it's in free stream already. So this term going to 0. Okay, so this will be this equation 4 is what's left, the integral form of the momentum equation. Okay, so this is the integral form of the momentum equation we have. This. Let me write it. This go to 0. This go to 0. And this go to 0. Okay. So this is how we derive the momentum integral equation. And similarly, we can derive the energy integral equation. It's same idea. You're using continuity equation times temperature on the both sides and added it to the energy equation. So you got this equation here. And you integrate this equation on y direction from 0 to y. And also notice that you have the following boundary condition. At the y location, there's no velocity, there's no u velocity, there's no v velocity. At the wall, there's no u velocity, v velocity. At the y location, you have the temperature equal to T infinity. At the wall, you have the temperature equal to wall. And also at the y location, there's no y direction gradient because it's free stream. So you just added the that's do integration on this equation. So it's also 0 to y for this ut term, and you keep this d over dx. And this partial y term you have will be Vy Ty minus V0 T0. And because it's free stream, V will be 0. And also at the wall, there's no V value, so it's also be 0. And this term at the y location, because there's no gradient, no gradient on y direction at the free stream, so this will be 0. So these two terms is only the terms left. These two terms here. And also we try to add some add back this T infinity a constant term. It won't change the result. Just make it represent as a temperature difference. So this will be equation 5 will be the final form of the integral form of the energy equation. Okay. So now we have these two integral equation available, equation 4 and equation 5. So we have this equation form for this is the momentum integral equation, integral equation, and this is the energy integral equation. All right, and also we know that this mu, this term mu of partial u of partial y at 0. Actually, it can be equal to tau w over rho. Okay, because we know that tau w is mu of partial u over partial y at the wall. Okay, so we know this. And also, this term here is alpha partial t partial y equal to 0. It can also be written that, let me write it here, because we know that minus k partial t of partial y as 0 equal to q of w prime, wall heat flux. Okay, we can calculate the wall heat flux by using this Fourier's law. And we know that alpha equal to k over rho Cp. Okay. So basically, this can be written as we can write this as let me check it. I write it correctly. We see this term can be written as qw prime minus qw divided by rho Cp. Okay, so this term can be also written in this way. So these two integral equation can be rewritten as this two way: tau w over rho equal to this one, qw prime prime over rho Cp equal to this one. These two equations. And after we derive this integral form of equation, this equation here, we want to solve, right? We want to solve that what the tau w will be, what the qw prime will be. And to do that, we need to know the profiles of this temperature profiles and this velocity profiles. So basically, to solve this equation, we require the profile shapes that approximate the velocity and temperature profiles inside the boundary layer. This is always happened for the integral method, right? Remember that in the laminar boundary layer theory we do before, after we develop this, after we develop the integral equation, we also assume that this velocity. We also need to know that what's the velocity profile, right? I just want to remind you a little bit so you know what we are doing here. Remember that in this before, when we have this laminar boundary layer, we have the velocity here. This is u velocity. When we want to solve integral equation, we want to know this profile of this velocity here. We have several ways to do it, right? Remember that we can just assume that u over delta, equal to, equal to x or something. Just assume this is a straight line. Remember, we can assume this is a straight line, or we can assume this curve as a cubic polynomial, or we can assume that this curve is a sine function. If you know that notebook, if you read the textbook, but just by assume the different profiles of velocity with some functions. And also for the temperature field, I can also assume that this temperature profile with some known function. Although we do not know it, but we can assume it to be some function. After we assume these two shape functions, we bring to this integral equation. We can solve the result to get this value of tau w and qw prime prime. And we're seeing that if you approximate these profiles, not too bad. Basically, the result will be very good compared with the exact solution. And so we will do the similar thing here. We'll do the similar thing here. It's like we need to know what the to solve this equation, we need to know what the t of minus t infinity as a function of something, okay? X. And also we need to know that u as a function of x direction. We need to know this profile, x and y, sorry, not y, x and y. If we can find this profile, after we approach this profile, we can solve this solution. So how to do that? There are two ways to do that. One way I call it a simple solution of integral equation. Why is simple? Because that this way, okay, we do an additional assumption. We just assume that in these cases that we just assume that the momentum and thermal boundary layers have the same thickness. Basically, in these cases, we assume that this delta equal to delta t. Although that we know that this is only true when prime number equal to 1, right? We know that this is only correct when prime number equal to 1. But in this case, to simple the calculation, let's assume delta equal to delta t. And the u profile, we can assume that u over big U has this profile, y over delta times the 1 over minus y over delta. So the profile will something looks like this, okay? And you have peak in the middle somewhere for the u velocity. So if this is y direction and this is x, so this u profile will be something like this. And for the temperature profile, we assume that is T minus T infinity divided by T1 minus T infinity. So basically, the temperature profile with this y of x will be something like this, dropping like this, okay? So this is T minus T infinity. This is U over U, okay? T minus T of T1 minus T infinity. And this is the only value between y between 0 and delta, okay? When y is larger than delta, and basically u will become to 0, and t will become to t infinity if y is larger than 0, y is larger than delta, okay? You substitute these profiles, u, t minus t infinity, or tw minus t infinity, into these two momentum equation 4 and 5. No, into this equation 4 here, and the equation 5 here. And you solve it, you can solve what this delta value will be. You will see that this delta value is a function of the Prandtl number as well as the Grashof number. And after you solve this delta value, and because we know that you can also calculate the temperature profile. After you calculate temperature profile, you can calculate the gradient, temperature gradient at the wall, and you can calculate heat flux, and you can calculate Nussbaum number. So Nussbaum number will also be a function of the Prandtl number and Grashof number. So this is the one simpler way that to solve the integral equation. Okay. So the reason it's simpler is that we assume that the momentum and the thermal boundary layer has the same thickness. So we only have delta here. There are no delta t at all actually, and we assume this simple profiles. So this is the simpler way to solve, and the complicated solution way. So there is another way. Okay. So in this case, the momentum and thermal boundary series has different thickness. Okay. So in this case, delta is not equal to the delta t. And in this way, we need to consider two cases, right? when the prandtl number is very large or prandtl number is very small. Why? Because that the profile is different. Let's go back. Because this is a profile when the prandtl number is very large, right? The U profile and U profile and temperature profile. And this is the profile when prandtl number is small. This is the U profile and the temperature profile. They are not the same shape, okay? So that's the reason that for when you solve the integral equation, you also need to consider the two cases, the high prandtl number cases and the low prandtl number cases, because that they have different shapes of function. The U profiles you use for the high prandtl number cases, you cannot use it for the low prandtl number. You have to assume different shapes. So in this case, this is what the textbook use, okay? What our textbook use, that the U profile will be equal to exponential form minus y over delta times 1 minus e2 minus y over delta t. Okay, so using this one to represent that double layer shape for the U velocity. And for the temperature profile, it's just exponential to minus 1 over delta t, just the one direction attenuation. And it will working between 0 to y to until to infinity, because that is using the exponential form. Okay, and now the question is this, okay? If we do this shape function, how many unknowns we have? We do not know this big U. Okay, we do not know what the maximum of the value of the induced velocity U. U is unknown. We do not know delta, and we also do not know the delta t. So we have 3 unknowns, and we only have 2 integral equations. Okay, we only have the momentum integral equation, equation 4, and energy integral equation, equation 5. 3 unknown, 2 equations, so we cannot solve the problem. We need an additional equation to solve it. How we can do that? So how we can introduce an additional equation? So this is the idea, okay? Think about that integral equation. How we derive this integral equation? We derive integral equation by do the integration of the momentum equation and the energy equation on control volume. That control volume is between y equal to 0 to y equal to a larger y value, right? Big Y value. And then that means that the result you get, this integral equations result you get, the result, these 2 integral equations, equation 4 and equation 5, is only an approximate of your governing equation, okay? Because I hope you understand what I'm talking, because that, let me go back to here. Because we do the integration between 0 to y, okay? So basically integration is like a bulk method, okay? We integrate over an area, right? We try to get the bulk result. So after we got that integral equation, this integration will only know that what the average things, okay, inside this whole control volume. What the bulk value of this control volume results. Okay, the details inside this control volume, if I want to know the results inside in the middle of this control volume is missing, because you do integration. That means that your result won't contain the info inside. You only contain an overall bulk result. Okay, so basically the result any result inside this any point inside this control volume, like the velocity, the temperature, you won't be able to know it actually. That's why we need to assume the profile, because you do the integration, the things inside you'll miss actually. And we said that we need to add the third equation, right? So the way to add the third equation is that we just can try to select a point in the middle inside this control volume, so that add a conservation equation for it at the point inside, so that because this is what is missing from these integral equations. Okay, so one way to do this, to add the third equation to solve that problem, is that we can consider an equation that let me see how I can see it. Okay, so consider is that at a no slip layer where that 0 belong to y belong to 0 plus, which means that if you have this wall, vertical wall here, we consider a region point very close to the wall, the fluid point very close to the wall. Okay, so what does that mean? It means that this point very close to wall, between 0 to 0 plus. 0 plus means that it's very infinitesimal distance, okay, from the wall. And at this point, because it's very close to wall, which means that there's no velocity, right? Because the viscous effect is very close to wall. So that means that in the three terms for the momentum equation, the convection term, the buoyancy term, and the friction term, okay? Because no velocity, that means that the convection term is gone. Okay, only the buoyancy term and the friction term exist. So this is this equation I added here. Okay, so this is also add the no slip layer. Okay, we try to add an additional momentum conservation equation. Okay, this is the momentum conservation equation. So we added the detailed momentum conservation equation inside some point of this control volume to give the third equation. So this is add the y equal to 0 because it's very close to the wall. Okay, so now we have the third equation here. Okay, so you substitute these two assumed shaped function for the velocity and temperature, and for you have these three unknown function to the equation 4, which is the momentum integral equation, equation 5, which is the energy integral equation, and equation 6, this new added additional equation here. And your u delta t, these three unknowns can be solved. Okay, although the procedures to solve these three values will be very tedious, and I just give you the results from the textbook. It will turn out that you know, the textbook, even the textbook, they didn't give the detailed result. Okay, the textbook basically saying that this big u value, this u unknown value, will be changing with x over 1 or 2. Okay, and this delta value will be changing with x to the power of 1 over 4. And this delta t is also changing with x over 1 power 4, 1 over 4. And so this q value, which represents the ratio between the velocity boundary thickness to the thermal boundary thickness, boundary layer thickness, can be solved, you know, implicitly by this equation. You need to find the root for this equation, okay, if you know the Prandtl number of fluid. So basically means that this is only a function of Prandtl number, okay? This q. So the ratio between delta and delta t is only a function of Prandtl number. It depends on the fluid properties, what fluid you have. And it can be solved by implicitly by these correlations actually. And the final Nussbaum number of this integral solution will be a function of this q, is a function of these q terms. Basically, is the Prandtl number terms, okay? Because we know that q is the Prandtl number terms, and this Rayleigh terms to the power of, sorry, this is a typo. This is x. Okay, 1 over 4. Okay. So this is the case for Nussbaum number is sorry, Prandtl number is much larger than 1. And also for low Prandtl number fluids, we just assume different shapes of shape function, okay? So in these cases, we didn't using delta, okay? We just using delta V, that a small, distance between this velocity peak to the wall distance, okay? To the wall distance, this is delta V. Okay, this is U. So we assume this one, and also temperature field is zero, similar before. You substitute these two equations to the number 4, 5, 6, you can get the similar results. So which is U will be will changing with square root of x, and delta V will changing with x to the power of 1 over 4, and delta T will also changing with x over 1 over power 4. And similar things, the ratio between delta V over delta T is also can be this is also only a function of Prandtl number. Okay, it's only determined by the Prandtl number. Can be implicitly solved by this one, by this equation. Okay, and the Nusside number is also again okay contains the overall local Nusside number will be contained this Q term, and the Q term basically is that Prandtl number. Okay, the Prandtl number term and reading number term. So this is using a complicated way to solve the integral equations. So in this integral equation, like basically for both large Prandtl number and small Prandtl number cases. Okay. Okay. So any question here? So we finish here. We finished the integral solution of this natural convection case.
Yeah. What's the difference between the two U's?
Which two U? This small U? Oh.
Yeah.
This small U is let me show you the profile in the previous page. Okay. So this smaller U basically is this profile. The whole profile is a function changing with this on y direction. Okay, it's changing along this inside the layer. And this big U basically is this maximum value from here to here. This is big U. Okay, smaller U is just a whole profile. You understand my question? Do you understand my answer?
Yeah. Okay. Thank you.
Yeah. So just consider that U is just a scale unknown. Okay. That's the reason we're saying that this U is one of unknown, right? This U is unknown here. And this is the U, just over this largest scale is maximum value basically for this U actually, for profile.
Okay.
Yeah. So this is the integral equation. And the last thing for this integral method is that looking at how we assume the shape function. Looking at, we assume that temperature is T minus T infinity divided by T wall minus T infinity, right? What does this mean? We assume the shape function means we're using this T wall here. Basically, this means that the procedure we use here is only for constant wall temperature. Okay, because when we assume the shape function, similar things, okay, we assume that T wall here minus T infinity, which means that we know the T wall already. Okay, you only can do this if you know the T wall, because T wall is known. So that means that this is all the solutions we go from here. This simple solution integral method, complicated solution of integral equations for both case 1 larger Prandtl number, case 2 small Prandtl number. They are all for the cases where you know the wall temperature. Okay, so all this all this above is for TW equal to constant case, because we know that the wall maybe has multiple maybe has different type of boundary condition. The two typical one is the wall temperature is constant. Another typical condition is wall heat flux is constant. Okay, not for QW prime equal to constant case. Okay, it's not for this one. Now the question is here, how we can do, so if we change the boundary condition from the constant wall temperature to the constant heat flux temperature, so what should we do? So, you know, what we should we do for the constant wall heat flux cases? The way is very simple, okay? In that cases, when you assume the shape function, you cannot using this TW minus T infinity anymore, okay? You have to changing it to the some other cases. Remember that how we calculate QW prime? QW prime equal to minus K partial T of partial Y at 0 location, right? And it basically means that if you do scaling, which means that is order of K of delta T of delta T. Okay, so that means that when this is constant, when the QW equal constant, actually a corresponding delta T scale can be represented as delta T will be equal to QW prime times delta T over K, right? So that means that because when we try to assume the profile, we just using T minus T infinity or delta T scale, right? So in this case, it's delta T scale. In previous cases, delta T scale is TW minus T infinity. But in these cases, you have to change this delta T to this value, something value here. Okay. And that's why is that you see that we do that. I see that I see some literature. Okay, some other textbook they using QW prime prime times delta T divided by 2K. Okay, the reason why I have they have 2 here, my guess, okay, is because this. Let me show you. The reason why we have this 2 here. Remove this. We do not need this. My guess is that if you look in the temperature profile, you see that their temperature profile basically is like this one, right? Like that's this curve. I didn't draw it correctly. Let me redraw it. Let me draw it in a better way. So this is a wall. This is a y direction. And if the temperature field maybe something like this one, return to 0, things here. And if you want to represent the delta T, so this is T of wall, this is T of infinity here. You want to introduce the delta T, and this distance here, this, it's really not good. So this distance here, from here to here, this is delta T, right? And because this curve is not a straight line, I'm talking. So I think I guess what they are doing is that they assume that if you draw a straight line here from this, because we only need to know this partial T or partial Y as a gradient as a Y equal to 0, right? So the gradient here is more important. So if you draw a tangent line here, it will locate something here, okay? Basically, if you draw a tangent line here, as this partial T partial Y equal to 0, want to know the tangent, this distance is only half, is approximately half of this delta T. I'm talking. This distance actually is a half of the overtangent because this profile is not really a straight line, okay? It's a exponential form or something. So I think that's the reason the reason they added 2 here, because that they think this is more accurate. But it really should not affect the result too much. Okay. So basically what I mean is that if you have the constant heat flux, okay, all you need to do is just like to change this assumed temperature shape function, replace the TW minus T infinity to this value QW prime and times delta T or 2K. Then you can continue your calculation. Okay, that's the only thing you need to do. So this is if you have the constant wall heat flux is how you do the how you can do this integral solution. In our textbook we didn't cover this part. Okay, so I cannot give you that what the solution looks like actually, but this is just a general idea how you can do. Okay, so now we finished the integral solution. So let me see how many minutes we have. Okay, we still have like 50 minutes. All right. So one thing I want to let you know, okay. Actually, if you go over this, go through my lecture notes, it's a little bit different with your textbook actually. The difference is that in the textbook, okay, let me write it here. In the textbook, the textbook using this as the x direction and using this as the y direction. The plate direction as the y. This is the textbook. And in my lecture notes, you'll see that I'm still using this as the y direction and this as x direction. If you read textbook, you need to realize this. So the lecture notes I show in here is different. The way I define the coordinate xy coordinate is actually inverse of the reverse of the textbook. The way textbook define. I prefer this way because I still using y direction as a perpendicular to the wall direction, because that later on, okay, we will also consider the natural convection not only on this vertical flat plate. We have this G here, not only on this. We will also consider that natural convection on the flat plate, where you have this G, but you have this you added the heat here. What is going looking like in talking? Okay. I want this XY direction. In this case, you will definitely still note this as X direction and note it as Y direction, right? I want we have some, consistency between the two cases, and also maybe in some cases if the wall is inclined, not the 90 degree perpendicular, is inclined with some angle, like theta here, and you have this G velocity here. And in this case, I also still want that in this case, here is the X direction on the plate direction, is on the Y direction on the plate direction. I just want all the three cases you have the consistent XY notation. So that's why I reverse the X and Y from the textbook the way to this note way. Okay, so this is this note. So when you read the textbook, you need to realize this. All right. We finished the momentum equation. So sorry, integral solution. And the last topic of this class is similarity solution. Similarity solution, we go over similarity solution for the flow over flat plate, right? The laminar boundary layer. So the basic idea is the same. We just what the similarity means. We just assume that the velocity and the temperature profiles are geometrically similar, differing only by stretching factors in the x direction. What does this mean? So let me go to that profile. Okay, this is a good way. This is not doing. Yeah, let me use this one. So what the similarity means, right? So at this location we have this velocity profile like this one. So if I choose another direction here, what the velocity profile will be maybe something like this one. Maybe the scale is larger than this one. The maximum value of this delta t is larger, but their shape is similar. Along the x direction, all the shape of the velocity is same. Similar things for the temperature. Maybe at this location, the temperature profile will be something like this. So this per shape, because this delta t size and the delta t size is here, the boundary layer thickness is here and here is different. So this profile is different, but their shape is different. Their shape is still same, the temperature shape function. So this is what the similarity means. Let's go back to similarity solution. So to do the similarity solution, remember what we did in the laminar boundary layer? We assume first we assume phi stream function, okay? The reason we want to use this stream function is that, after you define u with partial phi, partial y, and v equal to minus partial phi, partial x, basically your continuity equation, this partial u over partial x plus partial v and equal partial y equal to 0, will automatically satisfied, right? Auto satisfied. So basically means that by doing this, you do not need to solve the continuity equation at all. So remember we have 3 equations, and by doing this, by using the stream function, actually you only need to solve 2. So you remove 1 equation already. Okay, and also for the temperature field, we're using this dimensionless form. We define theta equal to T minus T infinity divided by T wall minus T infinity. Okay, you bring this U, V, and theta value to the governing equation we have. The governing equation is we have after we do the Bosnisk approximation. So bring those U, V, and theta value to these 2 equations here, the momentum and the thermal equation. And basically, this is the momentum equation will look like. Become the all the UV value, UV terms is changed to the stream function terms, and you will have this, and also this term is coming from this theta value because originally is T minus T infinity. Now we add this theta times T wall minus T infinity. And also the energy term, the temperature term, we can do non-normalization based on this one to change it to the theta term. And also we have additional T wall over dxy. This term is usually 0, okay? If wall temperature is constant, okay? So this term is only exists if this dt wall or dx is not equal to 0. So we have these 2 equations. Now the next task is to find the similarity variable. Okay, so we assume the phi, the stream function, will be equal to alpha times f of eta times this Rayleigh number to the power 1 over 4, which this similarity variable eta will be y over x times the Reynolds number x over 1 over 4. Okay, and with this eta value and with this assume the shape function for the stream function, you can bring this phi to those UV value. You can divide it. You can know that U will become equal to this value, and V velocity will be equal to this value. Okay. And let's continue. The final form, okay. The final form of the equation, governing equation, will become this one. This is for phi f, and this is for theta. So this will be a 3rd order, right? ODE on f. I say ODE is ordinary differential equation because f is only for function of eta. Okay, so this 3' means that you do 3rd order derivative on eta, and also this you have the 2nd order ODE on theta. Okay, by doing this similarity, by substitute this similarity variables into this governing equation, we convert the partial differential equations to 2 ordinary differential equations. Okay, that means that it's much easier to solve, And since it's third order in the ODE on F and second order ODE on the theta, we need 5 boundary conditions, 3 for F and 2 for theta to solve. So this is give the meaning of the, because at y equal to 0, u equal to 0, what does this mean? Because at y equal to 0, u equal to 0, and u equal to 0 means that f prime has to be 0 because u equal to this one, right? U this one. So u equal to 0 means f prime equal to 0. So that's why you have f prime 0 equal to 0. At y equal to 0, v has to be 0. That means the f equal to 0 to be 0. That is because that, because f prime equal to, because we know that f prime 0 equal to 0. This is already 0. So to make v equal to 0 at y equal to 0, so this f has also to be 0. So this gives us f0 equal to 0. And for y going to infinity, u has to be 0. So we have this f prime infinity equal to 0. And for t equal to tw and t infinity as y equal to 0, y infinity, we have theta 0 equal to 1, theta infinity equal to 0. So we have these two ODE and 3 boundary conditions. So we can just solve it numerically, okay? So what the result looks like? So this is the theta solution for the theta. And the x coordinate is eta, the similarity variable, and the y value is theta. So basically, this is, you can think like this is the profile, the temperature profile inside the boundary layer, okay? Because the eta is indeed a location in y, if the x is fixed at a point, okay? So this is just like the temperature profile in the boundary layer for different Prandtl number. When Prandtl number is large, or when Prandtl number is small. So basically, when Prandtl number becomes small, you have much larger thermal boundary layer thickness. And this is the velocity result, f prime, because that you already know that we already seeing that because f prime basically giving you the u velocity at the fixed x location, right? So f prime, so you can look at this f prime result just like the shape function of the u velocity inside the boundary layer. So it's you can see that this is like when Prandtl number is small and when Prandtl number go to large. You can see that the velocity is increasing first and then decreasing. So this is that double layer behavior we saw before. We reach peak here, reach peak here, reach peak here, reach peak here, reach peak here. Okay. And again, okay, we can know that the larger the Prandtl number, the larger the boundary layer thickness looks like. So this is because the similarity result, we only have the numerical solution, okay? So we cannot write it in an exact form. So we're usually using this plots to represent what the solution looks like. You should be able to, our textbook do not have it actually, but I know that some other textbooks, they have a chart, okay? That you can, if you want to know the detailed result for your eta value and a Prandtl number, you can go to that chart to find what the theta value will be, f prime will be, theta prime be, and f prime prime will be, f prime 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 will be. Okay, I know that some book has this, so that you can using those charts to directly obtain the exact solution. Okay, after you get the temperature solution and temperature profile and velocity profile by solving this similarity equations, okay, by using this similarity method, we can post-processing the result we get, okay, to relate it to a Nusselt number, okay. So basically, Nusselt number at a location x can be calculated as h of x over k will be equal to minus theta prime at eta equal to 0, the gradient at equal to 0, times the radius number to 1 over 4. You can derive this yourself. It's very easy actually to derive. So yeah, maybe I should write it. The way to derive it is h of T1 minus T infinity will be equal to minus k dt of dy at 0 So basically telling us H over K will be equal to minus of d theta of dy at 0. And then we can do this by d theta over d eta times 0 times d eta over dy. And so this will be minus theta prime at eta equal to 0. Is this term here? We got here. And this one will give you x over 1 real number 1 over 4. So you put this x on here. You put that x on here. So you get Nussbaum number equal to this one. Okay. So after you solve the theta profile, you can calculate Nussbaum number. So this table gives you that for different Prandtl number, what the Nussbaum value will be. So for Nussbaum number will be. And also we have the limiting case, okay, limit case. When the Prandtl number goes to infinity, very large Prandtl number, we see that the Nussbaum number is only, depends on the real number to the 1 over 4. This result agrees with our scaling analysis we did before. You remember that scaling analysis table we did before? That this number is only dependent on this one. And when Prandtl number go to another limit, go to the 0, Prandtl number almost to 0. So this will be the local Nussbaum number will be, looks like, so it will become 0.6 times the release number times the Prandtl number to the power 1 over 4. So this is also, this term here is also agrees with the scaling analysis we did before for the case when the Prandtl number is small, what the Nussbaum number will be. Okay. And sometimes, okay, the local Nussbaum number is not what we are interested in. Okay, we are more interested in the average Nussbaum number for the whole plate for the whole plate if the plate has a height of h. So you can do the averaging. So the average Nussbaum number for this limiting case, when Prandtl number equal to infinity, you get this correlation. And when Prandtl number equal to 0, this average value between 0 to h, you get this correlations. All right. So any question here, guys? Hello?
No question.
Okay, because you guys are really quiet here. So this is a similarity solution. How we derive, because it's we didn't go too many details, okay, because we omit a lot of procedures in the middle how to derive this equation, because the procedure is the same as previous one we did in the laminar boundary layer theory. And the solution is again, okay, we have to using the computer to solve it. And after we get the solution, basically we can, we can do a little bit of post-processing to get the Nussbaum number. And also, actually, we can also do the post-processing to get the, after we know the f prime value, we can also do the post-processing to get the, what the friction force will be, what the tau W will be. But I cannot find it in the textbook, so I won't be able to show you here. So because the textbook only contains this Nussbaum number result, actually. Okay, and again, the last one thing we want to topic is that go back to look this boundary condition. Look at this boundary condition here. T equal to TW equal to at y equal to 0. What does this mean? This means that again, okay, similar to integral solution. The solution we get here is only for T y equal to constant. Okay. The curve we got here, the result we got here, the chart we got here is only for TW equal to constant. So it's not for the constant wall heat flux case. So what if we have constant wall heat flux case? What should we do? How we obtain the similarity solution? Okay, so this is last one. So this is a constant wall heat flux cases. Again, okay, in these cases, we know that the wall heat flux is order of K over delta T over boundary layer thickness. And based on our scaling analysis, this sub-boundary layer thickness is equal to this one here. This is the scaling analysis we did before. Let me show you. Let me show you what's the case. So Prandtl number larger than 1. Okay. So this is the scaling analysis we did here. Remember here, this one? If when the Prandtl number is larger than 1, delta T equal to H over real number to the -1 or 4. Okay. And this is where we have here. Because the scaling analysis doesn't relate to the boundary condition. Okay. So scaling analysis is working for both cases. TW equal constant or QW prime prime equal to constant. So we have this one. So we write this real number out, the form out. And okay, we have this delta T here, and we replace the delta T with this term, with delta T here. Basically, is delta T equal to QW prime prime delta T over K. Okay, we replace this delta T to this one, and then we can define a new Rayleigh number. We call it Rayleigh number star. In this new Rayleigh number, we didn't using the delta T to define the Rayleigh number. We're using this special delta T here, which involves QW prime prime and this K here, and also a delta T here, and delta T somewhere. Yeah, because delta T scale is moving on the left hand side. Okay, so we have these things here. So we define a new radius number, and let me write it down so maybe we can calculate it. So delta of T will be equal to H times this G beta, this delta T H sans H2 cube to alpha of mu times this QW prime delta of T over K to -1 over 4, right? And then you have delta T on the both sides. So you move this delta T on the left-hand side. So this will be coming to the delta T times delta T times that, so it will be 4 over 5, right? 4 over 5. Okay. And divided, and you have H here. Oh, maybe I should not do this way. It looks not good. So, but the basic idea is that you have delta T on the both sides. So you move this delta T from right to the left, and you move this H inside, and and also by redefine this radius number. Basically, you can see that your delta T can be scaled as this. Basically, you can get this result here. You can, after you move this delta T on the left, and you can get this delta T is only scaling to this H times this modified Rayleigh number, and this modified Rayleigh number is defined by this way. Okay, and then because from this correlation here, delta T is is a scale of this QW prime prime times delta T over K. So this delta T will be Q prime prime over K times delta T, and you bring this value to this delta T here, and you know that this delta T for these cases, for this constant heat flux cases, the delta T scale basically is this one. Okay, and then you have this delta T, you can define the Nussbaum number. Because QW prime over delta T, you get a film coefficient, you get the Rayleigh number to this one. I hope you, this is a little bit maybe I go through this part too fast. Let me remove it. Remove it. Okay. So the basic idea is that if you have the uniform wall heat flux, you need to switch you need to calculate the delta T scale from the Q prime because that your wall temperature is not constant. And by doing this scaling analysis, we will finally find that the Nussbaum number basically will be equal to this release number to modify the release number to 105. Remember that previously what we did that for T wall equal to constant, we have this Nussbaum number H will be equal to release number H of 1 over 4. Okay, so if you compare this one, so and this one, if Q W prime equal to constant, you will see that the difference is that if you change the definition for release number, and this power is changed from the 1 over 4 to 1 over 5. Okay, so this is what when you have the uniform heat flux, what is the result looks like. So this is for Prandtl number is much larger than 1. Okay. Here we only do the scaling analysis. Okay, we didn't get the detailed result that exact result that was a similar integral result or similarity solution. What is this uniform wall heat flux has, what it will be? Just some scaling analysis. So if its Prandtl number is much smaller than 1, and similar things, okay, you can follow the same idea as here. Basically, the idea is that in this case, the Nussbaum number H will be Ra of H Prandtl number to 1 over 4. But now, in this case, it's Nussbaum number H will be equal to Ra times Prandtl number of 1 over 5 star H. Okay. So, but the basic idea is that after you do the scaling analysis, we find that okay, the changes is this power term from 1 over 4 change to 1 over 5 if you redefine this release number. So this is what we know for the uniform wall heat flux. Okay, any question?
Yeah, for the TW constant for the Nussel H on the bottom for Prandtl smaller than 1, is that just 1/4 or negative 1/4?
You mean which one? Sorry, I lost what you're saying. So you mean
in the table?
In the table? Yeah, this is T wall equal to constant.
The bottom row in that column, is that a negative 1/4 or just normal?
Let me erase it to rewrite it. I know that I didn't write it correctly. It should be positive. So this will be N of U of H. You can I just regroup the result here. You can also find all this scaling analysis from previous slides. So
thank you.
Yeah, you just rewrite it here. So this will be R A H Prandtl number to 1 over 4. Okay. What's the number? Okay. Yeah. So the difference, the only difference, the scaling result is that two things. The power term is changing from 1 over 4 to 1 over 5, and also the definition of this release number is different. One is using delta T, one is using this QW prime. That's the only difference here. Okay. All right. So this is the last page I have for today, and before we finish, because a lot of students coming later to the class, and so for exam, I didn't finish the grading yet. So, but I promise by next Tuesday, you should be able to see your you find your midterm grades on the Blackboard. I will post your grades on the Blackboard. The second thing is homework. because now we're changing to this online teaching way. Before we have homework every week, but I don't think it will be efficient like we have every homework every week in these cases, because that when you submit the homework to me by email, I need to print it out, and print each people's homework and grade it. So I decided that, for this second part of the semester, so I only give you the homeworks for each chapter. Okay, so like maybe if this chapter we need 2 classes to finish, so maybe we will have homework after we finish this chapter. So for today, we won't have the homework, and we almost finished this external natural convection, but we have a small part left for it. It's like because right now for this lecture we focus on the natural convection on a vertical plate. So there are other forms of natural convection, right? As I told you, that natural convection on a flat plate, natural convection on an inclined plate, natural convection on a plate with the blowing and or suction, which means that the velocity at the wall is not 0. Or maybe some other cases like the natural convection around a sphere or something. I don't know if I can go over it, but we will finish go over some of these cases for next lecture, and then we will go to the natural convections for the internal flows. Okay, so basically we will have our homework next class. Okay. All right. Is this clear?
Yeah.
Okay. Okay.
Yes.
All right. So so let me thank you for you attending this lecture. You know that definitely this is not the ideal case that we want to learn, right? We want to go through, handling this class, but the situation is just, it's not easy. The outside is really dangerous, and it's not a joke, okay? For this virus and stuff, people are dying. So just, stay safe, and I will do my best to help you for this class. If you have any question, you can just write me an email, or I will still hold my office hour every Tuesday, at 2 to 3 p.m. I have my Skype information posted on showing on the modified syllabus. So if you want to find me, you just download that Skype for Business from the Stony Brook Software Hub, okay, and log in with your Stony Brook ID, and you just search my name, and you can find me. And if you have a question, you can just talk to me. I can, we can do the video chat or the voice chat to go share the screen to go over any question you want to ask. Okay. And another thing is that because this is the first time I try to teach this online class, I'm not sure the way I'm doing here is that I show the notes on the left-hand side and writing some notation on the right-hand side is, is good for you guys. So if you have any suggestions that how I can improve it, you can just write me an email to let me know. So because I want to improve my teaching, for this scenario. Okay. And also by tonight, I will upload the video for this class, and also this lecture notes, the PDF file, to the Blackboard for you to review. Okay. All right. Thank you guys for coming. I will see you next week.
Thank you.
Yeah. Bye.
Okay.